Hello and welcome to the Average Electronics Concepts of Electricity. This will be a supplemental lab to Electronics Learning Lab. We're going to specifically be covering current, voltage, and resistance. I wanted to kind of expand on these concepts before moving further into our workbook, mostly because I didn't quite understand it. And for anybody joining in that also doesn't understand, I think it might be a better option to just kind of cover some of these concepts before moving forward. And so it's going to be a slightly different little format that I've got going on. Normally, I've got this big circuit board in front of me, but this time I'm going to be utilizing Google Docs, and there's going to be no math here. It's just going to be covering specific concepts, specifically how does electricity kind of flow and what are the different components of what makes electricity flow. So first up, we're going to go ahead and start with what is a, oh, come on, man. I'm a little nervous. I'm going to go to the page break, circuit. So I find where I'm at, how I'm doing this. I hope everybody's doing well. Welcome. I once again had a little bit of technical difficulties, unsurprisingly. It's what I do. So, what is a circuit? Um, if you said it's a racetrack, you're not wrong. But specifically, a circuit is a closed loop that carries electricity. I'll get there. I say closed loop mostly because if you have an open-ended loop, I don't believe it's actually going to do anything. And I say that because if we think back to our previous modules that we did, our switches, whether or not it was the push button switch or the DDP, um, those ended up being open switches, meaning when they were open, the circuit did not complete and the sound didn't buzz or the light didn't turn on. Whatever it was, it didn't actually do what we thought it would be doing. Well, actually, it did exactly what we thought it would do. But that is the concept of an open loop. Your light switch that is on your wall that powers your fan, your light, whatever it might be, will go ahead and when it's off, that is open, and when it is on, it is closed. When it's closed, that allows the electricity to flow from the negative side all the way through to the positive and pushes the current all the way through. We'll expand on that as we go. So a current is the flow of electrons in a circuit. We could also say it's the flow of electricity, but specifically it is the flow of electrons. Now, let's see if I can if I can do this appropriately, I try to do a brief little run through um, to see how this would work out. We're going to go ahead and do a drawing. This is going to be a little ghetto, but hey, it is what it is. Let's go ahead and start with the circle. No, we'll start with the lines. So we've got our positive, and we've got our negative. Imagine this is our power source or our source. This can also specifically be a battery. Come on, if I can line that up. It's going to be in a circle. I know I'm doing a very good job right now. Let's line it over. We're going to send you to the back. Beautiful. Let me see how this is looking. We are. Good luck, Ellie. I hope you enjoy your raid. Thank you for joining in the meantime. So right here, we've got our positive, we got our negative, we got the circle around it. Just assume that this is a battery, but in actuality, this is just technically a power source. It is any kind of source. And we're going to go around, and we're going to go ahead and complete our circuit, right? Actually, let's make this a little bit longer. This is going to be incredibly rough, so I do apologize if you're expecting perfection. And so this right here is actually a circuit. Um, Super easy. You've got your positive at the top, you got the negative. Power technically flows. Can I do this? I wish I can edit this on the fly. Uh, I guess we could just do it this way. So naturally, we've got our, this is our circuit. I already said that. And to expand on what a current is, which is the flow of electrons in a circuit, we want to see if I could do it this way. Let's see what that kind of looks like. So we've got our positives. And imagine this pipe, this tube, this wire, if you will. Oh, that's not what I wanted. We want to circle. And send it back. I would use hotkeys, but my setup is a little funky. So for the sake of this, we're going to have multiple positive electrons here, right? And for every positive electron, we have a negative. So let's do this. Actually, we're going to make you smaller. The reason why I'm going to make it smaller is generally your negative electrons, from what I understand, are actually smaller um, than your positive ones. Is that going to work? Nope. I didn't do a very good job of making it smaller. These are just like minute details, but they bother me. Come on. We're gonna do another line. In my dry run, this went way easier. It should have just saved the picture as it was. All right, so now we got our negative. And for the sake of this, our one electron has one orbiting negative electron. I think that's what it is. And so when you complete the circuit, your power actually flows this way. That's not the arrow I was expecting. There we go. So your power actually flows this way. It actually flows from the negative side through to the positive side. And so when that happens, you're looking at a change. Come on, buddy. We've got the arrows. They're more. Nope. And so for every change, come every change. And so when the power starts flowing, it's coming from the negative side, flowing to the positive, and for every second or every millisecond or in a period of time, your negative electrons skip to the next positive one. So they kind of all shift down. And so this creates a current. Um, this current is what actually generates the not generates the electricity, but this is what feeds the loop. Um, and so this is actually described as. Do I have text here? This is described as the electron current. Electron, if I could spell it. Okay. And so generally this is actually how the how buddy. Difficult time with these arrows. Like to stick. So many smells. All right. Well, so that's the electron current. It goes that way. Now, I guess in electrical engineering, as I have come to read, um, they don't generally do the math in this regard because if you're doing math, if you're calculating your algorithms and whatnot for voltage, for current, things like that, specifically current, you would actually be dealing with negative numbers the entire time. And dealing with negative numbers, while is easy enough, especially today with technology, it creates a lot of extra noise, things that you have to calculate extra. Now, instead of having to deal with that, because you know that the negative electrons are always skipping forward, you can assume, or not necessarily assume, but you can reverse that and say that the positive electrons are actually moving backwards, right? Do I have an arrow? Nope. Are actually moving backwards. So when trying to calculate current, it's easier to calculate the current based on the positive values to get better whole numbers. And this is actually called whole current, right? Super straightforward. You think of a whole number. Excuse me. I can't remember. It's like my first time using Google Drive, which is, Google Docs. Completely false. I'm just slightly nervous. Um, and so the whole current moves backwards. Thanks, buddy. Okay, and so in electrical engineering, I equals whole current. I don't want a capital I want a lowercase I, and I want to move you. Right? And so specifically, it goes this way. As we have, oh, come on, man. Just hate me. So, let me catch up here. Whole current. Um, yes. Okay. So, recapping. Negative current generally flows negative positive. The reason is I don't actually know a good reason as to why it is. I think it's just because that's just the way electricity works and how electrons like to jump from the more positive electron. It is attracted to a greater mass, which fuck, I'm now getting outside of what I actually know. This is supplemental. I'm still learning. I apologize if I say some incorrect things. Please correct me if you know that I'm incorrect. Um, so yeah, this is this is the flow, or this is how a current functions. We're going to go ahead and save this. Let's make you a little bit bigger, right? And to expand on what a current is, we've got a base unit of ampere. Amp or A. So if you ever see a power supply or anything like that says it's 15 amps or amperes or 15A, and basically that is the amount of current that flows through the pipe. All right. Does that make sense? I hope so. Um, if not, please write me a comment or comment in the chat, something like that, and hopefully I can maybe go over this a little bit further, or maybe you can teach me something that I am incorrect on. Both are fully acceptable. So after that, we actually have our voltage, which is the push. So a voltage is the push that causes the current to flow. And its base units, or base unit, is volt or V, right? Um, so to expand on this, you can have a battery that is 1.4 volts and it has a current or an ampere of 50. That's not necessarily going to hurt you. Like, let's say a double A battery, the ones that are in the learning lab, are 1.2 volts, right? And so that is the amount of force, or the amount of push that battery can feed through initially into whatever the pipe might be. And so, despite the fact that it may have 50 amps, it's not enough to, let's say, kill you. Versus your car battery, which is, I don't know, 12 volts. It is large enough so it has a bigger capacitance to push an initial amount through that wire or through that pipe. And so, despite the fact that it may have the same amperes of 50 amps, it is far more lethal than a regular battery. Does it make sense? I hope so. Saying that out loud now, I don't know if that actually makes sense uh, to me. I would like to expand on that maybe a little bit further. Um, Hopefully, there's going to be some questions um, so that I can better do research and yeah, correct that. Okay. Next up, we're going to go with our resistance. Well, I don't like capitals. Your resistance. And your resistance opposes the current flow in a circuit. So its base unit is ohms, or what's that special format? I literally just did this beforehand and there we go, especially. Oh man. Omega. And this symbol is known as the capital omega. If I can get to it. Oh, hey, I should probably look at that. And so your base unit for resistance is measured in ohms or a capital omega, which is a Greek letter, if you're unaware. Um, and what's nice about, uh, I guess I should expand on that. How do I explain that appropriately? I literally had my notes and I'm failing to find it. Um, Basically, okay, sorry, I'm now catching up. You can have your natural resistance, or you can actually utilize something called a resistor. Um, but basically, the thicker the wire or the thicker the pipe allows for more current to flow through it. However, there is a maximum amount of current that can flow through a, a specific pipe or wire. Or we'll just say wires from now on. And that's why you have different gauge wires. Like let's say a 16 gauge um, will have a max amount of current that can flow through it versus a 24 gauge. The smaller the number you go, the the less current that can flow through it, and therefore the more natural resistance or the more resistance that naturally occurs in that set of wires. Um, I hope that makes sense. My preliminary run was so much better than this, and so I posted the card. Imagine you have a toilet paper roll or a paper towel roll, If you blow through that, you put your mouth to one end and you blow. That is your current. That's the amount of current that can flow through that. However, if you can measure that amount of breath that you're exhuming out of your lungs, and you move to a straw, and you try blowing through a straw with that same amount of force or that same voltage, you're going to have a natural set of resistance. It's going to be much more. It's going to be much harder to push that energy or that electricity, that force through that straw because it is much smaller in diameter, right? And so that is your resistance. Um, Now, to expand on this, your current voltage and resistance all exist with the metric system or metric prefixes. And so, say amp can be MA for milliamps, for milliamps, or let's see if I can get a insert special character, micro. This will be your microamps, right? Um, and then you've got your kiloamps, etc. For let's go ahead and use R omega, which can be again a I jumped on. Let's do V for volts. It's not nearly as exciting. There we go. And once again, we'll have the millivolts. And we've got the and so on and so forth. So I hope I am explaining this okay. I am now worried that I am not. So this will be your milli resistance, etc. I hope that makes sense. Does it make sense? Um, you get your standby. I want to expand on something in a moment, but I want to make sure that I have the correct information before I do so. So this will equal 1,000th thousand of an amp. While this is equal to 10 6. Shit. I'm not sure I'd actually do that. 10 minus 6. Uh, 1,000,000th. And then we've got our kilowatts, which is like that. Which is 10 to the third. God damn it. I mean, oh shoot. And the same goes for the rest of these. The math will always work out. Whether it's a volt, a resistance, or an amp. It's always you got your milliamps, 1,000th, 1,000,000th, 1,000th, which is 10 to the third, and yeah, neat. Um, I think this is all I'm going to cover. I hope this made sense. I feel like I may have confused some people. I may have confused myself. Um, yeah, let me know what you think. Please provide some feedback on this one. I wanted to provide a little bit more insight uh, into some of the concepts we were going to have. I unfortunately think I did this a little prematurely or incorrectly. We'll find out. Anyways, hey, thanks for joining. Have a great day. Have a great night. Be safe, be well, stay healthy. Bye.